Assalamu alaikum, sir.
Walaikum assalam rahmatullah. So how are you everyone? Today's proceedings. So in the last class, we were discussing about the issue of instability that may arise with the incorporation of exciter dynamics into the single machine infinite bus system dynamic model. Specifically, the issue arise when the gain of the exciter block is enlarged, okay, beyond a certain limit. So if the gain of the exciter block or the automatic voltage regulator block is not that high, I mean, if we look into this block specifically, so what I'm talking about is this. So this is the block. So if this gain Ka is kept to a very low value, then there won't be much trouble with the small disturbance stability. But as we said, we want this gain to be high to achieve some good steady state response. So that's why we kept it high. And we saw that as we kept on increasing the value of Ka, after a certain value of Ka, the system became unstable with respect to small disturbance stability, of course, because we saw that the eigenvalues were shifted. They were initially on the left half of the S-plane, but slowly they were shifting to the right half. So the complex poles were moving to the right half. And as soon as these poles, they cross to the right of the S-plane, then it is unstable. So then at the end part of the last lecture, I mentioned that, well, we will take some countermeasure to get rid of this instability issue. And we will start that topic today. So basically, we will be designing the PSS. In today's lecture, we'll be seeing at the design procedure for the power system stabilizer. So to begin with, we will be looking at the configuration of PSS, the different blocks associated with the PSS, and then we'll be going through some mathematical calculation procedure that will aid in understanding the design procedure for the PSS. And then we will be incorporating this PSS dynamics into the fourth order model that we derived in the last class with the exciter dynamics. So this block diagram over here that we are seeing right now, that is figure number 3. This is what we developed in the last class, the Phillips-Heffron model. So we have 4 states, and these states could be taken as the output. So from here, this is one of the states, that is the deviation in speed input. So you can measure it, you can observe it. So you can add some scopes here for looking at the output or the pattern of the output, variation of the output with respect to time. This is the phase angle or the torque angle for the generator, or the rotor angle of the generator. Basically, this capital delta again means this is the deviation in the actual delta variable. So again, this could be one of the outputs. This could be one of the outputs, del omega. This could be one of the outputs, that is del EQ prime dash. And this could be one of the outputs. So you have 4 states. And if you have the available facility to measure all the states for any certain physical system, then you can measure all of this. You can make them observable. And there are 2 inputs, like this is the del PM. This is the input that is coming from the mechanical input side for the generator. And this is the deviation in the exciter field reference voltage, or the voltage regulator set point. So deviation in the voltage regulator set point. So these are the 2 inputs. So it is a 4, you can consider it to be a 4-state system. And again, the number of outputs is dependent on the designer's choice. But there are 2 possible inputs that you can play with. And in this case, actually, both of these inputs are treated as the disturbance inputs. Okay, these are not control inputs. These are rather disturbance inputs. But the input that we will actually obtain from the PSS block, that would actually be one of the control inputs that would be actually added at the input summing junction for the exciter block. Remember, this block is the exciter block. So if you if you can recall the exciter block, probably it's not here. So the exciter block was, we were always looking at the exciter block like this, or the AVR block. With the help of the block diagram, we were always mentioning that there is a del P, del VS, one of the inputs in the summing junction. So there were several inputs in the summing junction. One was del VREF. So one was coming from the load compensator, and we took it as the same as the terminal voltage of the generator. So we took it as the same as the terminal voltage deviation, the linearized form of the terminal voltage variable. Then another one was del VREF. This is the reference set point, or the change in the reference set point. So this was plus, this was minus, and this was again plus. And the third input was actually the UPSS, simply UPSS or del UPSS, whatever you say. You can erase the U part. So simply it has to be understood that UPSS is a linearized version of the output from the PSS block, power system stabilizer block. So we'll be talking about the generation of this signal today. So there are many ways actually to design the speed power system stabilizer. This is one sort of a controller block, okay, controller block. So in the controller block, as we all know, that there should be some error fed to the input of the controller. So let's say if this is the big building block for the PSS, this is the input side, and this is the output side. So from the output, ultimately, we expect some signals named as UPSS. At the input side, it depends on the choice of the designer again. So there are many choices available in the literature. One of the choices is the speed input. That means for the linearized model, it would be delta omega. The other choices available are, of course, should be mentioned here. So another choice could be del delta. That is one of the state variables there, of course. And another choice could be del PT, or change in power flow. Okay, generator change in the generator real power output, del PT. So in short, these three could be, any of these three could be used. But in today's lecture, what we will do, we will use the speed input for the design of the power system stabilizer block. However, the same design principle, same method could be used for any other kind of inputs. Of course, the mathematical relationships should be changed accordingly. So let's start the design process. Our main target is to bring back the stability to the system that became unstable with the introduction of this fourth state variable. And of course, for a large input here, Ka. So we'll keep the value Ka as it is, but then we will be adding up the dynamics for the stabilizer. And then we will check the stability, whether after designing and incorporating the power system stabilizer to this fourth order system, whether our target is achieved or not. So let's start. So to start with, we have this fourth order model. Again, we have the fourth state variables, one, the del delta, del omega, del EQ dash, and del EFD. So there's a system matrix A. So this is X dot equals AX plus B. This is the input matrix, B into U. Again, this U is nothing but a vector of the disturbance variables. Okay, so the PSS block that we are going to adopt in today's lecture, there could be a variation in the number of blocks that are used to represent the PSS. So one option is to use only a single block. By this block over here, we are referring to this middle block. So we're talking about the lead block. So there could be either one block, two blocks, or even more than two blocks. So in general, there could be n number of blocks, n number of lead compensation blocks, okay, or this block. How to choose it? We'll take it slowly as we go through the lecture. How to choose the number of blocks, okay, how to choose it. So besides this lead block, we have a gain block. It's a pure gain block denoted by KPSS, and we have another washout block. Each of These blocks has its own job. So let's start with, let's say the middle block, as we mentioned it at first. So the lead compensation block, basically it provides the required amount of phase lead necessary to compensate or to counterbalance some phase lag that is produced by the electrical loop. Okay, what is the electrical loop? We mentioned it in the last class, probably at the end of the last class. So let's take it again. Is the electrical loop and what is the mechanical loop? Because these two keywords will be appearing every now and then in today's lecture. So the upper block comprising of, or the block which is providing the two outputs like del omega and del delta. So this block is referred to as the mechanical loop, the green one, this green dashed block. And the one at the bottom, which provides two outputs there, which both of which are electrical, like delta EFD, specifically both of them are actually voltage outputs or change in voltage outputs. So you see in the electrical loop, both the outputs are of electrical nature. Okay, delta EFD, this is the field excitation voltage deviation, and delta IQ dash, this is the transient Q axis internal voltage deviation. So both of these two outputs belong to electrical quantities. So this is electrical loop, the blue one, the blue dotted one, and the upper one is the mechanical loop. So you can clearly see that, as I said in the last class, also I mentioned it today, that with the incorporation of this block over here, this block over here, and with after a certain value of Ka, after a certain numeric value of Ka, what it does actually, this block injects some signal which passes through these blocks along this line, and it injects some torque at this summing junction. Why it is known as torque? I mentioned it in the last class. This, you remember, in the per unit system, all of these, most of these variables used here are in per units, except some few of them, like del delta is actually in radians or degrees. Other than that, most of the units are per unitized. So in per unit system, actually the power and torque, these are interchangeably used. Okay, they have the same units. Power and torque could be interchangeably used. So that means this input is nothing but could be treated as, also treated as delta Tm. Okay, the same as delta Pm. So this is nothing but a summing junction which is taking different kinds of torque inputs as and then it is summing up everything appearing at its junction. So that also means that this K1 del delta, this is also one sort of, this should be also another sort of torque, and anything coming over here, that is K2 del EQ prime, this should be also another sort of torque expression. And this torque is actually coming and creating problem, causing problem once we have this high gain AVR over here. Otherwise, it was not creating any problem. Whenever the system was third order, there was no such problem for the parameters taken under consideration. But once we introduce this and we started to increase Ka, then the effect or the impact of this torque was such that it changed a stable system into an unstable one. So that's why we are trying to look into the cause, actual cause or background cause for this instability. And we can say that this signal actually that is coming from the Ka, effect of Ka, is fed through this path into the summing junction in the form of torque. That is actually creating some lag. We'll calculate the lag actually later on. But this is the basic that we are trying to explain here. So these blocks, this block Ka over 1 plus Sta and this block 1 plus K3 Sto prime, they combinedly, and of course this K6, this is a closed loop. Remember, this is a closed loop with negative feedback with K6 del EQ dash coming over here, minus K6 del EQ prime coming over here. This is a negative feedback closed loop. Also, the upper block is a negative feedback closed loop. The mechanical loop is a closed loop with negative feedback at the summing junction is appearing as minus K1 del delta, minus K1 multiplied by del delta. There's a minus sign. So the lag that is introduced by this exciter block has to be taken into consideration, and we have to try and negate this lag. Okay, get rid of this lag. So to get rid of this lag, what we would do, we would incorporate some lead effect, phase leading effect. So this is the reason of bringing some phase lead block over here. So this is the explanation why we actually need this lead block. So in short, we want to get rid of the lag introduced by the electrical loop and injected into the mechanical loop. Any question about this? Okay, no question. So let's proceed. So this is the purpose of the lead block. And this is the basic transfer function model for the lead block. You have two time constants, T1 in the numerator and T2 in the denominator. So if it has to be worked as a lead block, simply T1 has to be greater than T2. If it is a lag block, then the reverse should be true. T1 should be less than, sorry, T1 should be less than T2. If it is a lead block, then T1 should be greater than T2. That means the same representation could be used either as a lead block or as a lag block. Because we are in need of a lead, then we have to ensure that T1 is always greater than T2. Okay, so the gain block, that means this block over here, the gain block, job of the gain block is to produce sufficient amount of damping to the unstable system. Okay, remember the system that we are taking into consideration, initially the system is unstable. We are assuming initially the system is unstable. That means we are assuming the gain value Ka to such a magnitude that would drive this system into instability or unstable zone. And then we are trying to design this PSS to bring back the unstable system into the stable zone. So that is the target. So that means we saw in the last class that we had some positive real part eigenvalues with some positive real parts, and that was giving some negative damping effect, negative damping eigenvalues with negative damping. So that's why we have to ensure that sufficient damping is introduced with the help of this power system stabilizer block, and that should be positive damping. Okay, to counterbalance the negative damping introduced by the delta EFD block, we have to introduce some positive damping with the help of this block over here. So KPSS will ensure that the desired damping or sufficient damping has been introduced by the PSS block. The third block is the washout block. Its job is simply, it would work as the high pass filter. Or in another way to say is, whenever there is any transient, whenever the system is in transient condition, this will work. However, whenever the system transient dies out, then it shouldn't do anything. It shouldn't interfere with the dynamics of the system. So that's why the name is washout block. Okay, it works simply as a high pass filter. Okay. So these are the three blocks, and then the number of blocks required. The number of blocks required actually depends on the amount of phase lag introduced by the exciter block. Okay, again, how many blocks would be here required here? Will it be, will only one be sufficient, or should we use two, or should we use more than two, or what? It depends the amount of phase lag, this lag produced by the electrical loop, and that is injected ultimately to the mechanical loop. So we have to find out how much lag is actually produced or introduced by the electrical loop. When we get that information of the magnitude of the lag, then we will be in a position to determine that how many blocks would be required by us. So that could only be told after a certain part of the calculation of the design has been done. Okay, so whenever the time comes, I will again mention that how many blocks we would need, and then accordingly we will continue the design. So if it is a two-stage block, simply you have to use two lead blocks. So accordingly the time constants has to be updated. So for the second lead block here, you may use T3 and T4. And of course, you can design for half of the lag. Okay, you can go for probably a single block design. Let's say the lag is 70 degree, let's say, for example, but you may actually choose a certain limit, let's say 60 degree, for example, or 50 degree. So there is a certain standard for that. So let's say the maximum that can be covered, for example, by a single block, the maximum lead that can be covered is, let's say, 60 degree. But however, you find that for your system, the lag introduced by the electrical loop is beyond that 60 degree. So let's say it is 70 degree or 80 degree, something like. So in that case, you have to go for two blocks and so on. However, you can use two identical blocks. You can design a single block, and then you can say that, well, I designed it. So if your lag is 70 degree, what you can do simply, okay, first decision is that you have to use two blocks. That's fine. But what you can do, you can simply make it a 35 degree lag, and you can design a single stage power system stabilizer. So what will happen ultimately by designing, we mean this, you can get the values of KPSS, T1 and T2, all these values, and then that is done for the single block. So then what you will do, you will simply set T1 equals to T3 and T2 equals to T4. So for 35 degree, you design a single block, lead block. For 70 degree, you simply assign these things so that you don't have to go for further complexity in your calculation part. So you can make them identical just by making T1 equals to T3 and T2 equals to T4. And while designing, just simply take half of the actual lag. So let's say it is 35 degree. In this way, you can get quick results. Okay. So we will start with the one stage power system stabilizer design. So this is the Phillips Heffron model that we already said, and output of the PSS block actually will arrive here, which is not shown here, but we'll show it later on. So the output of the PSS block will actually come here. So this will be your PSS. And because this is speed input type PSS, as mentioned earlier, so your PSS, if it is a single stage PSS, then ultimately you will get UPSS here. And your input would be del omega. So that means this del omega should be made available from here. So simply you have to take the sampling from here and you have to connect it there. So you take the del omega information available there, deviation in speed, and you feed it to the PSS block. That means this PSS block, if it is a one stage PSS, then so you can clearly see del omega is coming as the input, and actually this is your full, this is the full PSS block. So del omega is the input to the PSS, and UPSS is actually coming out from the PSS, the control output, control signal generated by the stabilizer that would ultimately go at this summing junction, here, at this point. So this is the UPSS. Okay, so now let's go to the steps slowly. So step number one, what we have to do. So what we have already done, we have actually identified that there are two loops. One is the mechanical loop and one is the electrical loop. Now let's go to the design process in a step-by-step manner. So step number one. So use the mechanical loop of figure 4. So first of all, what we are doing, we have separated the loops. So what to do that, what simply you have to do, you have to assume that these signals that are transferred from electrical to mechanical or mechanical to electrical, these signals are actually assumed to be not available. Okay, this transfer of signals are to be ignored for the time being. So, and another thing that you have to ignore is this damping. So assume that this D is 0. That means system damping is not present at all. So these are the assumptions. So first assumption, as I said, you don't assume that there is any interconnection between these two blocks. Second assumption is that you assume simply that there is no damping present in your system. So with these assumptions, what you do, what you will get actually is this block without any damping. So that means simply you will get rid of this D. D would not be there. So other than D, everything else will be there. So then what you will have is a loop, a negative feedback loop, with the forward gain being this one. Forward transfer function is this one, and this is the negative path transfer function. So if you are looking for the closed loop transfer function, okay, or the reduction of transfer function block, then let's assign it as we did in our undergrad level. So this is G of S, the forward path transfer function, and this is the negative feedback path transfer function. So this is H of S. So what would be output by input? Anyone? Output is del delta, of course. Input is del PM. So what would be the closed loop transfer function?
GS divided by 1 plus GS into HS.
GS divided by 1 plus GS HS. Excellent. So this would be the closed loop transfer function. So if this is the closed loop transfer function, and if we know that we have G of S expression available, we have H of S expression available, remember D should be assumed as 0, okay, in the design process of the PSS. So then you will get something like this, okay. So you'll get something like this over here. So I assume that is done. You should be able to get that. So if that is done, then let's continue. This is step 1. And now we assume that, well, let's say we don't have any effect from the external input. It means what? If you remember, there were two kinds of responses. One was zero state response. What was the other one? And there was another response, zero, then fill in the blanks. Can anyone recall? For any dynamic system, either you can go for the zero state response, or you can go for zero fill in the blanks response. Can you recall? Have you heard this term before or not? No answer. I don't know. Okay. So that is zero input response. Means the dynamics that you are interested, either you look at the stored energy within the system, okay? You look at the stored energy within the system, that would be actually zero input response. Means to drive the system dynamics, to initiate the system dynamics, you assume that there is no external force, no external input, but whatever dynamics is there is completely due to the initial value of the state variables. This is what is called zero input response, okay? So input is 0, U is 0, disturbance input is 0 in this case, but the initial state values are non-zero, okay? So as we are representing states with the help of X, so X zeros are non-zero, at least some of them, if not all. So this is the configuration for obtaining zero input response or analyzing zero input response. For zero state response, the reverse will happen. Means here the initial state variables will be 0, but the input should be non-zero. So the system dynamics will be governed purely by some external disturbance input. So when we say that considering, when we say this, considering zero external input means it is a zero input response. That means this one. Okay, del U is zero. So for our system, for the mechanical loop, what is the input? For mechanical loop, the input is delta PM over here. So we will assume that there is no external force that is driving the system dynamics. Rather, there should be some initial value of the state variables. So if that is true, then del PM should be assumed as zero. And you can simply cross multiply this expression over here and find out this expression. And then, of course, you can take del delta not equals to zero. That means, to simplify this, actually, if you want to get rid of this del delta, that for doing that, what you will do, you have to simply divide both sides of the equation by del delta. So because del delta is not zero, why del delta is not zero? Can anyone tell? Del PM is zero, that is assumed. But at the same time, we cannot assume del delta equals to zero. Why? What is actually del delta? What is del delta? Del PM is input, that is fine, no problem. But what is del delta?
X.
Sorry?
X. State variable.
State variable, state, excellent. So as we said, the initial value of the state variables, at least some of them, if not all, should not be assumed to be zero. So you see, we assume the initial input as zero. So at the same time, we shouldn't assume all the state variables equals to zero. So at this moment, at this point, we assume that del delta is one of the state variables, which is not zero. So if that is true, then we can easily divide both sides of the expression by del delta. Otherwise not, because otherwise if del delta is zero, we cannot make it like 0 over 0, right? That would become undefined. So that's why it is very important to identify which of the values here are zero and which are not zeros. Okay, so after cross multiplication, you see del PM is zero, so omega 0 will not appear in the expression on the right hand side. So simply it is 2h s squared plus omega 0 k1 multiplied by del delta equals to 0. Then what we do, we solve for s, but before that we make both sides divided by del delta. So we are only left with s. S is the root for this characteristic polynomial. So this is a second order polynomial. So simply it would give you two roots. And by the nature of the equation, it seems that both of them should be of complex nature. Okay. And the root general expression for the roots are like this: plus minus j omega naught k1 divided by twice of h. So this is the s, or the root for the mechanical loop that we have got. So this ends step number 1, and the conclusion from step number 1 is this, that this s is again nothing but what? Remember, this is the Laplace variable, which can be represented by this j omega, right? Actually, generalized expression is sigma plus minus j omega for Laplace domain, because this is the Laplace domain plot, sigma and j omega. However, because there is no real part associated here with s, so we can simply drop this sigma and we are left with some plus minus j multiplied by omega term. This omega is nothing but the natural frequency of oscillation. Okay, actually the angular version of that, omega n. Fn would be the exact name for natural frequency of oscillation. And of course, Fn and omega n are related by this expression. Fn is omega n by twice pi. So at the end of step 1, what we have achieved, we will achieve that at which frequency actually the system low frequency oscillation is being generated. So this frequency omega n here, this is omega n. This is nothing but the low frequency of oscillation that we are interested upon. Okay, this is very important to identify before we design the PSS. So in step 1, the job is actually to calculate the natural frequency of oscillation, omega n or Fn, whatever you say. If you know omega n, you can calculate Fn very easily. Okay, so we have this job done. Next, we go to step number 2. And now we, as we mentioned earlier, there is a phase lag introduced by this loop. There's a phase lag from here. And when it is injected into the upper part, into the mechanical loop, we want to know how much phase lag is there. Okay, so this is, with this we will take and step number 2. So in step number 2, we have shown actually the UPSS here. This is the position of the UPSS, or the signal where the UPSS would be actually coming up. And in figure 5, this is the electrical loop with the PSS signal. And we are interested on actually between the transfer function between this EQ dash as the output and this UPSS as the input. Or in other words, between this summing junction and this output variable EQ dash. So again, if you look carefully, this block over here in figure number 5, this is again nothing but another transfer function block having a negative path along this line. So you see K6 del EQ dash, there is a negative feedback path at this summing, the first summing junction over here. So again, what we do, we simply assume that del Vref is equals to 0. Okay, del Vref is equals to 0. We are not actually bothered about del Vref for the time being. And we try to find out the transfer function over here. Again, what is G of S here and what is H of S here? GS and HS. So what is the forward path? This is the forward path, the top one. So these two blocks would comprise the G of S. And this negative feedback path gain K6 would be the H of S. So again, if you are interested in finding out the closed loop transfer function between the output del EQ dash and the input UPSS, we can do that. The same formula, G of S divided by 1 plus G of S, H of S. So that is actually done here. So that is actually done over here. And again, you can derive it pretty easily. G of S over 1 plus G of S, H of S. So that is done, and we get the transfer function over here. And we call this transfer function as the transfer function for the exciter, just a name, G of X, GEX, G sub EX. But the transfer function is between the output del EQ dash and the input signal that is to be designed, that is UPSS, and this is the transfer function. Now this transfer function has to be evaluated because you see the presence of S here, okay? Presence of S. Let me make it a little larger. Yeah. So there's a presence of S, and we all know that S is nothing but J omega. Okay. But now this J omega, this is not any arbitrary omega. Rather, this omega should be the omega equals to omega n that we just found in step number 1, because that is our frequency of oscillation, the low frequency oscillation problem. That is the frequency associated with our instability problem. So we have to evaluate this G of GEX at a certain frequency that we calculated in step number 1, and that is nothing but omega n. So we have to evaluate this G of X at a certain frequency. So this bar here means evaluated at S equals to J omega n. And of course, when we replace S by J omega n, we would get some magnitude for this GEX, that is absolute of GEX, and some angle gamma. And this gamma is the lag angle gamma that we are interested on. So this is the lag angle produced by the exciter with a sufficient gain Ka. Okay. So this is the lag angle gamma. And this is the conclusion. If angle gamma is greater than 60, you have to use 2-stage PSS. Otherwise, you use 1-stage PSS. So this is a thumb rule, you can say. As a rule of thumb, this is used by the designers. Okay. So we have to know what is gamma, and then only then we can say how many stages of PSS or lead blocks actually. These 2-stage PSS means we are actually using two blocks of two lead blocks. Okay, the gain blocks remains as it is, the washout box remains as it is, only the number of lead blocks gets changed depending on the lag angle gamma. Nothing else changes. Okay, so we have got the information of gamma. We will get the information of how many stages are required at this point. Then this is the conclusion from your step number 2, that you have got the information of gamma and you will get the information of how many stages of lead blocks are required for your design. Then step number 3, we design the phase lead blocks, the form of which is represented by another transfer function GC. C simply means the compensator. This C means simply the compensator, and the form of the compensator would be like this. And you see the number n. N means how many stages you have, whether it is 1 stage or 2 stage or more than 2 stage or what. So n is the number of lead blocks required for compensation. By compensation means you are trying to compensate this gamma, the lag. So as the target is to completely wipe out the phase lag, what we would require to satisfy this constraint or this equation, that is the angle of GEX, simply this is nothing but gamma, plus the angle of this transfer function GC, they should add up to 0. So that would satisfy this term, this line over here, as the target is to completely wipe up the phase lag. For the next steps, as I said that we have few parameters to design the complete the design for the PSS. So these two are the time constants for the lead blocks. If it is a one stage PSS, then we have a gain to be designed, and of course we have the washout time constant. So these 4 things are to be designed. To start with, what we will do, we will assume some reasonable value. Again, this is thumb rule, you can say, between 0.02 to 0.15 seconds. Okay, so you choose this value, and then we start our design. We continue with our design. So let's continue with the 1-stage PSS design. So in the 1-stage PSS design, the form of GC would be like this. You have a single time constant in the denominator, T2, and the single time constant in the numerator, that is T1. T2 already we have chosen any value within this range. Then this is the condition that we have to satisfy. We mentioned it here. GEX plus GC, angle of both of those should be added up, and they should bring a 0 value. The angle of GC again has to be calculated. Remember, this is again a transfer function. But again, you see the appearance of S. So that means the same thing has to be done here. This has to be evaluated at j omega n, the frequency of our interest, not any arbitrary frequency. The frequency at which the low frequency oscillation problem has happened. So this is GC, angle of GC. So this whole thing is the GC expression that has to be evaluated at S equals to j omega n, and we only need the information of the angle. Then angle of GEX is nothing but gamma, and that should be 0. So then we have simply splitted the expression. Okay, so it is 1 plus ST1. Then the division angle that is appearing in the division denominator, that is coming up as the minus sign. So 1 plus ST1 angle minus 1 plus ST2 angle. Of course, both of them has to be evaluated at S equals to j omega n, remember, plus gamma equals to 0. Then this angle means nothing. If you have a complex expression like 1 plus j omega n, this 1 plus ST1 is nothing but this 1 plus j omega n into T1. So if this is your complex expression, A plus JB, what should be the angle? What should be the angle for this? The magnitude is, of course, 1 plus A square plus B squared. Okay, square root omega n squared T1 squared. This is the magnitude of the expression. What would be the angle?
Tan inverse
omega. B by A, right?
Yes.
B by A. So this is A plus JB. So simply it would be tan inverse omega n T1 divided by 1. We can write it, we can omit it. Ignore it, no problem. So tan inverse omega n T1, this is the angle. And we are interested in this. So you see tan inverse omega n T1, this is the angle for this one. Similarly, 1 plus ST2, the angle would be tan inverse omega n T2. And the gamma is taken to the other side, so that becomes minus gamma. And then in this line, what we do is simply take tan for all of these parts in this equation. So this becomes minus tan gamma, and the tan inverse term goes out. So we are left with omega n T1 minus omega n T2 equals to minus tan gamma. And then we are interested on T1. So here you can see why we had to choose actually T2 here. Okay, we have no other option. If we follow these steps of design, we have to start with some value of T2. Otherwise, we will be stuck here. Okay, this is the problem. That's why we chose the T2 value here. So now, because we have some assumed value of T2, then you can simply calculate T1. So you simply change the sides and you are left with T1, the required parameter. So this will give you the value of T1. Gamma is already calculated. This is the angle of GEX. This was calculated in step number 2. T2, it is assumed here. So that means you know everything here on the right hand side. Omega n is already calculated in step number 1. So all the previous steps data are actually required here to calculate T1. So at this step, you know, by the end of this step, you know what is T1, what is T2, and what is your omega n, and what is gamma. So all information are now available. All these information are available. So you are still left with KPSS. Remember, the job of KPSS was to introduce some damping, some desired level of damping. So we'll try to get the value of KPSS next in step number 4. So let's see. So what we do here, we are talking about some desired damping ratio. Okay. So again, that is a designer's choice. The design, how much damping you want to incorporate within your system with the help of PSS. So the job again is to design a gain block to ensure sufficient amount of damping or desired amount of damping. And this damping will be contributed by the designed PSS through the electrical loop and K2 to the mechanical loop, as shown in figure 6. So this is the figure 6. So you can see now here, everything is available. So you see, this is my one stage UPSS. So I will take del omega somewhere from here, the remaining part of my, okay, actually from the mechanical loop, this will come from within the mechanical loop. Then this is the single lead block. This is the gain block, and this is the output UPSS fed into the summing junction of the exciter block. And then this is the torque we are talking about. So actually, before this design of PSS, this block was not, okay, this signal was not available. So this signal was not available. So there was some negative damping torque being introduced to the mechanical loop. That was the problem. And that was created by this Ka value, high Ka gain here. So now in addition to that, what we are doing, we are incorporating some additional dynamics with the help of PSS, and we are injecting some other damping. Instead of that negative damping, now we are trying to design some positive damping effect through this path, through the same channel, but now with the help of PSS. So this is the channel now. So through this channel, the signal will be fed through the K2 gain block to the mechanical loop. So this will be the injection point. Okay, from electrical loop through this gain K2 to the mechanical loop into the torque summing point. Okay, summing point of the torque. So there is the summing point of the torque. So in the summing point of the torque in the mechanical loop, this signal will be fed actually, this signal. And this UPSS will only get activated, you can clearly see, when and only when this del omega is non-zero. As soon as this del omega becomes 0, the PSS shouldn't do anything to the dynamics of this or to the response of the system. Okay. So that means whenever the system is successfully able to get rid of any del omega, any oscillation there in the speed signal, then the PSS signal should die out or settle down to some equilibrium. Otherwise, PSS should be activated. That means in the transient situation, you have some del omega, you expect some del omega. That means that you expect deviation of your speed of your machine from the synchronous speed value. So in that case, the UPSS signal would be fed and the corresponding damping torque would be fed to the mechanical loop. Otherwise, when the system dynamics decays and settles to some equilibrium, the del omega shouldn't affect actually. Del omega becomes 0, so shouldn't affect anything here. There shouldn't be any contribution later on after that point. Okay, so this is figure 6. Now we again go back to where the point where we were discussing. So the figure 6 part we have already shown the figure 6. Now let's consider any second order dynamic system. Standard second order dynamic system can be represented in this form. Okay, s square plus 2 zeta omega ns plus omega n squared. This is already familiar to us. Now with the electrical damping, we treat this electrical damping, we denote this electrical damping provided by PSS as DE. Okay, this is the electrical damping, D for damping and capital E for electrical. The mechanical loop dynamics now should be updated. Okay, how it should be updated? And this is the updated equation actually. So remember what we are getting is a damping DE, and that means what you will get, remember we said that this D is not present. This is, remember, from the initial system damping. We started our calculation considering D, this D is 0. Now, when we are saying that we have some damping from the UPSS, and that is denoted by DE, simply what you will see that this D, which was actually 0 initially, now we will have a new DE coming instead of the initial D that was assumed to be 0. So now putting DE here, you simply recalculate this transfer function. Output del delta divided by input del PM. Recalculate the transfer function. And you should get, with this simple change, you should get this expression. Previously, in step 1, we used the same expression with D equals to 0. There was the D, but that is assumed to be 0. Now with this damping provided by the PSS, this will be the update. Okay, this will be the update. Why it is appearing here? Remember, any damping that is provided at that summing junction over there, at the initial summing junction over here, this damping can be included into the swing equation in the form of some damping power. And damping power is nothing but D, because it is electrical damping, we are denoting it by this form, DE multiplied by del omega. If you can recall it, this is the expression of the damping power. So you just incorporate it into the swing equation, you simplify that, you should get this block, 2HS plus DE. So this is how this DE is actually reappearing here. Okay, instead of D, this DE is coming from the UPSS. Or sorry, PSS, the PSS block. So this is how this equation will be modified, and it will now become identical . So wherever we were discussing load shedding problem. So okay, so we were here. Okay, so we were discussing this. Okay, so with the incorporation of this damping or introduction of this damping, our equation would be updated like this. Okay, so you can clearly see that again we are assuming del PM is equals to 0. but del delta is not 0. So we can divide both sides by del delta like before, as we did in step number 1. But simply now the change is here. We have some additional damping provided by the PSS. So this is the DE, and you can clearly see 2H is squared DES plus omega 0 K1. It can be made identical like this simply by taking out the coefficient here, okay, making the coefficient of S square equals to 1. And for doing that, we simply have to divide the whole thing divided by twice H. So now it is S square plus DE over twice H into S plus omega 0 K1 divided by twice H equals to 0. And now you can just make a similar conclusion from here. So if you just compare the coefficients for equation 2 and 3 respectively, then you will find that 2 zeta omega n is nothing but dE over twice H, okay? And omega n squared is omega 0 K1 by twice H. And interestingly, we get the same conclusion for omega n as we did earlier. If you compare these two, then what is omega n? Simply omega n comes out as whatever we got from our step number 1. And that is K1 omega 0 by twice H. So omega n remains same. Nothing is changed with omega n, the natural frequency of oscillation. Simply what we have introduced some damping, and we can compare by comparing the coefficients between equation 2 and 3. We can get this dE equals to, or dE by twice H equals to this 2 zeta omega n, and then simply dE would be 2 zeta omega n multiplied by twice H. So now this is the damping that we would get from PSS, okay? Now, because the washout block, the job of the washout block is not to provide any damping, so we can get rid of that. We can get rid of that block. By this, we mean simply when you calculate this, simply ignore this, because we are trying to calculate how much damping should be provided by UPSS. The job of washout block is not to provide any additional damping, okay? Its job is to only pass the high frequency signals, okay, not the low frequency signals. Only high, it is a high pass filter, so it will only pass the high frequency signals. So it has nothing to do with the damping, provision of damping. It doesn't provide any damping. So we can get rid of this washout transfer function while calculating or while trying to calculate this KPSS. So with this, we would get equation number 5. Okay. So in the equation number 5, what we have actually, we simply have dE equals K2 GEX GC into KPSS, and the magnitude of that. Okay. Remember, these are transfer functions. GEX is a transfer function. GC is another transfer function. GEX is the transfer function that we calculated in step 2. Similarly, GC probably we took it in step 3. Okay. So we have this, and again, these are to be calculated at the natural frequency of oscillation for our system. But how we are getting it? We are getting it because we know that along which path actually this dE would be transmitted from the UPSS to the mechanical loop. I showed it earlier. Let me show the path again. You are getting K2, GEX, GC, and KPSS. So remember these 4 terms: K2, GEX, GC, and KPSS. Now you look at this carefully. I simply dropped this. So you see, it is GC, KPSS. The whole thing over here is what? It is GEX multiplied by K2. So these are the 4 terms appearing there: K2, GEX, GC, KPSS. So this is the path. This is the path of signal flow. Through K2, it will actually affect the mechanical loop. Okay, it will go into the mechanical loop and inject some damping. So this is why these 4 terms are appearing there. So with this equation, then this equation being discussed, now we should be able to understand the remaining part quite easily. So then we simply take out the gain terms. K2 is a gain, so we just separate it from the remaining part. KPSS is also gain, so we separate it from the remaining part. The GEX and GC are to be calculated now again at S equals to J omega n. So from equation 4 and 5, what we can get, so this is DE, and this is another expression of DE. So now this, you see a zeta term over here, this is the damping ratio. And this is where the designer's choice comes. So now you have to select some value of desired damping zeta. And you set it equals to this zeta appearing in equation number 4. Then when you set it, then this becomes 2 zeta desired omega n into twice h divided by. So actually what we are doing, we're equating these two because both of them are DE. We are making zeta equals to zeta desired, and then we are simply solving for KPSS. So this is what you will get, equation number 6. So by the end of step number 4, you should be able to know what is your KPSS value. The only remaining thing is the time constant value T omega appearing in the washout block. And again, thumb of rule is simply take some large value like 5 to 10 seconds for the washout time constant. So once that is taken, then your design job is done. So this is a 5-step design process, and it is known as the phase compensation design process for PSS. Okay, but once again, there are many other advanced techniques for designing the PSS. I have just shown you as an example. I have shown you the phase compensation technique with speed input PSS design. So with the incorporation of PSS, of course, the dynamics would be a little bit updated because you have the PSS signal now appearing here. Okay, so this block now becomes what? This block now becomes the input to this block becomes delta EFD. So this is your delta EFD. This is the output. The input becomes del VREF. Of course, we are not too much interested in del VREF. Del VREF is there. So then it's minus K6 del EQ prime. Oh, there is another K5 del delta, if you remember. So that is in general actually minus del VT. So keep it general. So minus del VT, there is a terminal voltage deviation. Plus now you have UPSS. And that should be equated to your this transfer function. Ka over 1 plus STA. So this is the update. So you have a new variable here, UPSS, because it is being fed to this summing junction. So now the exciter dynamics would be a little updated with the incorporation of this UPSS signal. And of course, from this, out of these blocks, you expect some state variables. One of the state variables would be, let's say we assume it to be U1, that is appearing right after the washout block. So U1 dot, you will get some expression like U1 dot. And of course, there is some other S. Wherever you have S, you expect some state variables. This is a gain block, so there won't be any additional state variables due to this gain block. But UPSS, you will get some equation in terms of UPSS. So in total, your system dimension would be increased by 2 if you have a one-stage PSS design. Okay, so previously it was 4th order, now it would become 6th order with some additional changes here. Okay, in the exciter equation, exciter block equation. So when you do that, of course, you can, I hope you can do the calculation now of simplification, like U1 by del omega. I mean, if you want U1 dot, what you have to do, simply you take this block over here, washout block, as the transfer function between the output and the input. So output is U1, input is del omega. So 1 plus STW. And simply you cross multiply. So it would be U1 dot plus U1 dot TW. And then this would be del omega dot into TW, and del omega dot you have to replace from the previously written second state equation. Okay, del omega dot speed state variable. Then this one UPSS divided by U1 for this block. UPSS is the final state, so it would be simply KPSS. It is the gain block simply multiplied by 1 plus ST1 to 1 plus ST2. Okay. So in this way, you can cross multiply this, and you can replace the expressions for U1. There will be one U1 dot actually. So U1 dot will be available from this expression, and you replace it there, and ultimately you will get UPSS dot. And this U1 dot would be available from this relationship. So these are the two equations that you will ultimately obtain, two new state equations. And of course, you have to add these UPSS here. So the modified A matrix would be like this. So this is the one stage for a one stage UPSS design. You clearly see that you have two additional state variables. So your dimension of the A matrix becomes now 6 by 6. Previously it was 4 by 4. And this K by TA, again, this is appearing due to the presence of UPSS in the exciter summing junction over here. The next class, inshallah, I will show you the detailed derivation. Don't worry. And we will go for some simulation results. Okay. Just to make sure that whatever we are designing are actually fulfilling our purpose for PSS design. Okay. Any question? Anyone, any question? Okay, if you don't have any question, then we can conclude today's session. And similarly, of course, we can go for two-stage PSS design. I will not go into the detail of that. The same thing, you can go through the process that is mentioned here. Of course, if it is a two-stage PSS, then number of state variables would be further increased, and system dimension would be again increased further. Other than that, the only other change could be probably here. Okay, as I said, whatever angle lag angle is generated there, you simply divide it by 2 and assume simply that T1 equals to T3 and T2 equals to T4, and you simply design for one stage. That means you simply look for T1 and T2 values and KPSS values, and that is done. And then simply you take T1 equals to T3 and T2 equals to T4. That would do the job. Okay, then if you don't have any queries, then we can stop the session here. And see you inshallah on Friday morning. Okay, assalamu alaikum.